Hello everyone, my name is Jinha Jung. I'm an assistant professor in the Life School of Civil Engineering at Purdue University. Today I'm going to talk about UASHub, how to build a modern cloud-based data portal for the management of big UAS data. Before I start my presentation, I'd like to acknowledge my co-author of this presentation, Dr. Jin Chang, Dr. Marla Maeda, Dr. Juan Landiva from Texas A&M Mega Life, Allison, Gary, and Siva from Oracle Corporation. UAS, unmanned aircraft system, has been very actively utilized in agriculture application to develop a hard-to-put phenotyping system very recently. The way how it works is this UAS, and sometimes we call this a drone, is collect the very high-resolution data collected over the research plot. Then we use those data set to visualize the field, and we also analyze those collected data to develop agriculture application out of it. So this is overall workflow of how the UAS-based high-throughput phenotyping system is going to work. First, we need to develop a platform. It can be either multi-rotor platform, fixed wing. More recently, it can be the VTOL, vertical takeoff and landing system. And then we need to have a sensor. There can be a variety of sensors. It can be RGB, multispectral, thermal, hyperspectral lidar. And we need to integrate those sensors into the UAV platform so that we can collect the data out of it. Then we need to do the data collection, and actually we all need to go out to the field and collect the data. Then once data set has been collected, we need to transfer the data to the location where we can actually analyze it. And we need to pre-process it. We call the SFM, which is a structure from motion. That's the most popular algorithm that is being used out there to process optical images into a format where we can visualize and analyze it. Then we need to visualize those the pre-process the data. We call that level 1 data product. Then we need to analyze it so that we generate a high level data product out of it. Then finally, the end user need to be able to download those analyzed data set so that they can develop specific agriculture application out of it. So this UAS-based high-throughput phenotyping system is very intensive. The process that you need to go through to make this data product useful for the final agriculture application. There are two main big hurdles that we need to overcome for the workflow that I showed in previous slide to work. The first one is the fact that UAS data are big, and it takes a lot of time to transfer that big data from one location to another. To give you an idea how the big UAS data are, this is an example of UAS data collected within Texas A&M system for the last 6 years. X-axis is a year, Y-axis in volume in terabyte. As you can see, every year we've been collecting the data from somewhere ranging from 5 terabyte all the way to 30 terabyte, and we ended up accumulating all the way up to 115 terabyte data for the last 6 years. Another hurdle that we need to go over is going to be a data processing software. UAS data are not only big, but a lot of times they need a very specialized software. And as an end user, it's going to be very challenging to keep on track of all those complicated software installed on your machine. So in order to address those two big hurdles that I mentioned in previous slide, what we developed is something called UASHub, where all the UAV data and all the process in higher level data product is going to be stored in a centralized space. And we are going to be developing a custom developed server-side application so that end users can access all the data and the application just through the web service. Initially, the UASHub was implemented on Texas A&M AgriLab computational infrastructure, but we recently teamed up with Oracle so that we can implement the UASHub on Oracle Cloud infrastructure so that this framework can be adopted in other places very easily. And like I mentioned before, level 0 to level 1 is going to be mainly structure from motion process, where we have images with a lot of overlap. We can use different SFM software to generate the 3D model out of it, so we can have a 3D point cloud, surface model, and automosaics. And because this is in a very computationally heavy process, what we can do is we can use some of the parallel processing capabilities to speed up this process. As I mentioned in the previous slide, SFM, structure from motion, is going to be the most computationally expensive process in the UAS data processing. We tested the performance of SFM in 2 different environments in this study. And the first one is AgriLife cluster, which is going to be isolated cluster that is already implemented in Texas A&M AgriLife Research Station. And another one is OCI, which is Oracle Cloud Infrastructure. As you can see from the left slide, AgriLife cluster we tested with 2 different nodes. First one is equipped with the Intel i7 8700K CPU with a 3.7 GHz clock speed, and it has 32 GB of RAM on it, and it has a GPU of NVIDIA GeForce GTX 1070 Ti. And the first one is a little bit more powerful machine than the second one, and the second node is equipped with the Intel i7 4790K CPU with 4 GHz clock speed, and it has 32 GB of RAM, and it has an NVIDIA GeForce GTX 980 GPU on it. In AgriLife cluster environment, we tested 2 different storage options to store the UAV data. First one is when each of the nodes was utilizing local storage as a data storage, and another option is when they're using network storage as storage to store all those UAS data. The reason why we are testing 2 different storage options is because this is UASHub, which is completely integrated system where UAS data is actually stored in a central database, and we can actually come up with 2 different data processing storage strategy. First one is going to be downloading all those data from the central storage to the local storage, so that we can process it a little bit faster. And but we're going to be spending more time to actually download the data set to the local machine. And another approach is when you actually use network storage, so that to process the data set, so that we don't need to download the data from the central database. So that's AgriLife setup. On the right side, I'm showing a Oracle Cloud Infrastructure experiment setup, and we tested only 1 node for this study, which is equipped with the Intel Xeon 2.2 GHz and a CPU on it, and it has 72 GB of RAM, and it has a GPU of NVIDIA Tesla P100. And we are in the process of getting access to more powerful Oracle Cloud Infrastructure node right now, and we are in the we are planning to actually process this data set in a more powerful node on Oracle Cloud, and that will be updated later. And like I mentioned earlier, Oracle Cloud will have actually 2 different storage options. First one is going to be local storage, which means that we are going to be storing all the data on a local node to process the data. And for the network storage option, Oracle provide a various levels of the network storage option. We are testing 2, which is 5 storage, which is a little cheaper to use, but they have less bandwidth to transfer data back and forth. And the second one is block storage, where it's going to be a little bit more expensive, so you need to pay a little bit more, but you're going to have much better throughput in terms of reading network files. And these are some of the UAS data set we used for the experiment. We just used 2 different data set, 1 small and 1 large. And the number of images is the main difference over here. 203 images for the small data set. We have 1,500 images for the large data set. And the data size is this one is 4.7 gigabytes, and this one large data set is 25 gigabyte almost. and the rest of the other setup is quite different in terms of flight height, but in terms of actual data processing, more important part is going to be how many number of images you're going to be processing, how big they are. So these are the statistics about small and large data set. This slide shows result of small data set. The graph in this slide is showing processing time of each structure from motion steps in different colors, and those steps are shown at the bottom legend. These steps are align photos, optimize alignment, build dense point cloud, build DEM, build orthomosaic, and exporting DEM and orthomosaic images. As this graph represents the time it took finish all the SFM process, shorter bar in the graph represent better SFM performance. Let's look at the local storage option comparison. As you can see from the graph, OCI with the local storage option is performing better than node 2 of AgriLife cluster, but performing slightly worse than the first node of AgriLife cluster. When we look at the network storage option comparison, OCI with the block storage option outperform both AgriLife node with network storage options, while OCI with the file storage option took longest to process the small dataset example. This slide shows result of large dataset. As you can see from the graph, OCI with local storage option is performing much better than the second node of AgriLife cluster and performing almost the same as the first node of AgriLife cluster. When you look at the network storage option comparison, OCI with the block storage option outperform both AgriLife node with network storage option, while OCI with the file storage option took the longest to process the large dataset example, which is almost identical observation as the small dataset example that we discussed earlier. One thing I would like to comment here in this slide is the performance comparison between local storage and network storage within AgriLife and OCI. As you can see from the graph, OCI with the local storage option and the OCI with the block storage options perform almost identical, while AgriLife with local storage always perform better than AgriLife with the network storage option. We hypothesize that OCI with the block storage can give us almost the same throughput as local SSD drives, which is great. In the meantime, AgriLife network storage is interconnected with only 1 gigabit network switch, which cannot give us enough bandwidth to match the performance of local storage option. I believe OCI with a better GPU with the block storage option will give us much better performance, which will be confirmed in the future. To summarize, this presentation showed our progress on porting already operational UASHub on OCI infrastructure. SFM performance results show that very promising performance of OCI for UAS data processing. When comparing local storage options, OCI showed almost identical SFM process performance as the on-premise cluster with local storage option. When network storage option is used for the UAS data processing, OCI provided much more flexible options. OCI with the file storage option showed the slowest in performance, but it will cost the least. And OCI with the block storage option demonstrated slightly better performance compared to AgriLife node with the network storage option, but OCI can be loaded up with more powerful node to speed up the UAS data processing if needed. These results show that OCI could be a great alternative to implement UASHub for large-scale implementation because, first, OCI has low initial investment cost to start the project. OCI has on-demand cost structure, which means that you will be only charged for the hours the computation resources on the OCI is being used. For on-premise cluster implementation, we usually need to make capital investment for initial hardware purchase, but the OCI won't need the capital investment to get started. Second, OCI can provide industry-level security and hardware maintenance as a part of their service. Maintaining security and hardware specs can be daunting jobs, especially when small business would like to adopt this kind of technology for their breeding programs. Third, OCI is going to be scalable, which means that you can always start your project small when you are starting and add more storage spaces or computational resources as your project grows. For on-premise cluster options, increase your storage space or upgrading your hardware can be painful and costly process. There are many tools I was not able to include in this presentation, but we are working hard porting whole UASHub into OCI infrastructure, which I believe it will be completed by end of this year. Thank you for listening my presentation.